Good morning. Video 2 in our excursions into linear algebra. Um, this video is going to be all about definitions. I hope it doesn't overwhelm you. It shouldn't. What we're looking to define here is this thing that's called a vector space. Turns out that vector spaces pop up a lot in information retrieval. And what I want to do is I'm going to start with a vector space that you're all very familiar with, this thing called R2, as in R2D2, yuck, yuck, yuck. And maybe you've seen a definition like this. This is the set of all vectors that look like X and Y, such that X is an element of R and Y is an element of R. Okay, so for example, we would have that the vector A, 1, 2, that's an element of this thing. And we can have all sorts of other weird stuff. We could have a vector B, which is made up, the x coordinate is pi, and the y coordinate is e, for those of you that may know that. That's also contained in R squared. We could have a vector C, which is equal to the square root of 2, 3/2. That's an element of R squared. All of these things are in R squared. So there are a couple of things that I want you to note here. First of all, there's a very special vector called the zero vector. And that's contained in R squared. And that has a very special property that for any v that's contained in R squared, we would have the zero vector plus v is equal to the v vector plus 0 vector, which is just equal to v. Nothing weird about that. But we're mathematicians, computer scientists. We have to give it a name. Otherwise, I wouldn't have anything to quiz you on. We'll call that identity. There are a couple of other things to note in here. That for A contained in R squared and B contained in R squared and C contained in R squared. There are a couple of things that we first note. We note that A plus B is contained in R squared. Okay, and this is what's called closure. We also note that A plus B is equal to B plus A. And that has a name that's called commutativity. Okay. A couple of other things in here. We note that A plus B, and I put parentheses over there, plus C is equal to A plus B plus C. And you will note over here that what I've done is I've just changed where the parentheses are. This has a name. It's called associativity. Okay. I am going to leave this. I'm not going to close this slide up yet, but I am going to save it. I'm going to keep it over here. I want something else. I want to say that for any vector A contained in R squared, there is a unique vector B contained in R squared, such that A plus B is equal to B plus A is equal to this special thing called the zero vector. Okay, so that's not anything weird. We can see over here that this vector B is just equal to minus 1 times A. And this is called the additive inverse. Okay. For any vector A contained in R squared and any real number R, okay, which is contained in just that, we have that RA is contained in R squared, and this is just called closure of scalar multiplication and there is just one more thing to say here. For any A and B contained in R squared and any scalar R contained in R, we'd have that R times A plus B is equal to RA plus RB. A lot of stuff there, huh? So between everything that you see here, and when I say everything, I mean everything in this original slide right here, okay, and everything over here in this second slide. If I have a non-empty set that satisfies all these properties, it's called a vector space. Okay? So let's consider some examples of what is a vector space and what isn't a vector space. So first of all, we already note that this is a vector space. And it shouldn't surprise you that R3 is a vector space. And in fact, it shouldn't surprise you that Rn, for n greater than or equal to 1, any of those are vector spaces. Okay, maybe it's time to consider a couple of other things. Let's consider, I'm going to call this capital A. And I'm going to say, let this equal the set of all, and I'm going to call this alpha, beta, 0, such that alpha and beta are real numbers. So in a way, A looks a lot like R3, and in fact it's a subset of R3. We could certainly say that A is a subset of R3. But what I'm doing here is I'm insisting that the last coordinate here, some people would call this the z coordinate, I'm saying that that's 0. And I will leave it to you to follow all the exercises out there and say that A certainly is a vector space. What about this one? Suppose I were to come over here and I would say let B equal the set of all alpha, beta, 7, such that alpha and beta are contained in R. And the question is B a vector space? And B is not a vector space for a couple of reasons. First of all, we will note that there is no 0 vector in B. Getting news reports on my computer as I do this to you. Okay. The other thing to note is let's consider 2 elements in B. So 1, 2, 7 is in B. And let's suppose I were to come in here and pick something else that's in B. 3, 4, 7. Now I'm recognizing each one of these as vectors. Okay. But if I add these up together, I just add the components. And that's equal to, well, 3 plus 1 is 4. And I come over here and 2 plus 4 is 6. And I come over here and I add 7 plus 7. Well, that's 14. And that clearly is not in B. Okay? So B is not a vector space for a couple of reasons. First of all, there isn't a 0 vector in B. That's one reason. Number 2, B is not even closed under vector addition. Okay? So this is not a vector space. All right. Let's consider one more example. So let me close that up. Let me close that up. All right. Let's come over here and do the following. And what I'd like to do, let's consider, I hope I can draw this. So let's call this C, and I'm going to say let that equal the set of all x comma x, such that x is contained in R. So the point is what is in this set C? Well, 2 is in it. Pi is in it. Minus E is in it. 7 is in it. So one of the questions you might ask is 0 equal 0, 0 in this set? And the answer is yes. Is this closed under addition? Well, sure it is. If I were to take, for example, these two numbers right here and add them, I'd get 7 plus pi, comma 7 plus pi. That's still in it. If I were to multiply this by a scalar constant, that's still in it. So this is a vector space, yes. Okay, but let's consider one more example. Suppose I came over here now and I did this. And Again, please pardon my drawing skills, particularly working on a tablet. They're not great. This is supposed to be a straight line, and I think you can tell that this is y is equal to x plus 1. So for example, this is going to have 0, 1 is going to be on here, 1, 2 would be on here, 2, 3. And in fact, this is going to be equal to the set of all x plus 1, such that x is contained in R. And even though this looks just like the last line that we drew, except everything was shifted up 1, you can see the big problem in here. There's no zero, there's no identity in here. This thing is not here. It's not in this set. So the conclusion is this is not a vector space. Okay? We'll save it. And that is the end of this very short video.